Hello, welcome to Math 253, Calculus 3 here at Cañada College. My name is Lapuz. In this video we will go over a homework assignment from section 4.7. This is problem number 14. They want us to assume that our function f of xy is equal to x squared minus xy plus y squared minus 2x plus 2y. And given that function and our domain x squared plus y squared is less than or equal to 4, they want us to find the absolute maximum and absolute minimum. Okay, so I think they just want the values. So there are restrictions on whether you want to put the point itself or just the z values, the output values. And I think here they're just looking for the output value. Okay, to do this, this is an extreme value problem, which says that your maximums and minimums could happen either at a critical point or in the boundary. So let's, according to the algorithm, let us try to figure out what happens with the critical points, and if the critical points are within the boundary, then we're going to consider them. So let's find the critical points. First, we need to find fx. Let's use a blue color, f sub x, and that is a derivative of the function with respect to x. So that's going to be 2x minus y plus 0 minus 2, and we're going to set that equal to 0. And also we're going to set fy equal to 0. Fy is going to be negative x plus 2y plus 2. All right, let's set them both equal to 0. We got 2x minus y minus 2 equal to 0. And we have negative x plus 2y plus 2 equal to 0. Let's write it neater. We have 2x minus y equals positive 2. And negative x plus 2y equals negative 2. All right, I probably want to maybe multiply the second function by 2 so that the 2's would cancel, or the x's would go away. So the x's would go away. This is a negative y plus 4y. So that's going to be a positive 3y. Is equal to, if we add this is 2 minus 4, so that's negative 2. So y looks like it'll be negative 2/3. Now with that, I can plug this into either equations to solve for x. Let's put it into the second one, minus x plus 2y. That's negative 2/3. Plus 2 equals 0. So it's negative x minus 4/3 plus 2 equals 0. Negative x, the common denominator is 3, so this is positive 6. So 6 minus 4 is 2. And then we'll bring that over to the other side. It'll become negative. And the negative x will go away by making it positive, so this is positive 2/3. All right, so that is our critical point, and yes, in fact, the critical point does look like it'll be within the circle of radius 2. This is our circle of radius 2, our constraint. I said 2. And positive 2/3 and negative 2/3 would be the critical point sitting right around here, and we want to know what the value is for that. So let's put it into the function. F of positive 2/3 and negative 2/3. And so we will have, actually I'm just going to go ahead and use Desmos for this. And I'm kind of getting ahead, and this is eventually something that we'll do, but this is the function itself. So if I put in f of positive 2/3 and a negative 2/3, I get a negative 1.3. So I think that's 4/3, negative 4/3. So we'll come back to that Desmos file in a few minutes. But for now, this is our value. It looks like it's below the x-axis or the xy plane, so it might be a good candidate for the minimum. Because looking at this function here, it does look like an elliptic paraboloid that's been kind of, the ellipse has been shifted a little bit. Okay, so that's just one possible answer, but we need to find what happens at the boundary. Now, to find out what happens at the boundary, what we need to do is we need to express the boundary. So let's label, let's first label our work. This is critical points. And that's the critical point that we found, and then we found this as our possible max or min. Now let's go to the boundary. And the idea behind trying to do something in the boundary is to try to figure out what happens just at the boundary. Now there are other techniques that we can use to solve for that, but one technique is to parameterize the two-dimensional boundary and see what happens when you project it onto the surface. So let's parameterize the boundary. And we're going to parameterize it because it's a circle, radius 2. We can just simply parameterize it with sine and cosine. So it's 2 cosine t for the x, 2 sine t for the y. And we'll just remind ourselves that we're going to go from 0 to 2 pi. Okay, now that we have that, let's put it into the function. So f of r of t, which is actually just going to be a function of t, and let's be even more explicit. This is going to be the z value of that function of t, which is going to be, let's see, 2 cosine t, and the quantity squared is around the whole thing, minus 2 cosine t 2 sine t. So this is the x and the y. And then we have the y squared, 2 sine t quantity squared. And then minus 2 times x, which is 2 cosine t. And then we have a plus 2 times y, which is 2 sine t. So this is a big function that we want to deal with and find the max and mins. I'll simplify this a little bit, but I think to try to find the max and min of this, I would fall back on technology to help us out. Here, these two underlined terms have a sine squared and a cosine squared combination, and then there's a 4 that would come out of that. These two will give us a 4 cosine t sine t, and then we just have minus 4 cosine t, and then plus 4 sine t. So this is what we want to work with for our t values going from 0 to 2 pi. All right. I kind of worked on this a little bit and got this going here. This is the parameterization that we want, that we're using. And what I want to do is I want to put that into the function, the f of xy function for t values going from from 0 to 2 pi. And if I graph that, I see this graph over here. So this graph shows a few things. It shows a value here at 0, and a value here that's up high when theta is equal to 3 pi over 4, or t. And then it touches down here at 0 again, and then it comes back up, but not very high, at 7 pi over 4, and then back here at 0 at 2 pi. So these values give your maximum and minimum, and clearly the maximum is going to be at 11.656 or 657. The minimum looks like it's going to be 0, but remember we had a smaller minimum at negative 4/3. So I think the negative 4/3 will win as a minimum. Let's take a quick screenshot of this, and so we can talk a little bit more about this in our notes. This is our analysis, our max and min analysis of that function that we were working with. So I think this is the only thing worth discussing, because everything else, by the way, this is a t-axis. That's your t going around, and this is your z value. This is literally your z-axis, and so this gives the height. So we have t is equal to 3 pi over 4. And then if we translate that to our parameterization, our our cosine t and sine t, let me see this again. Yeah, if we put that into our cosine t and sine t, x is going to be the cosine of 3 pi over 4, which I believe is going to be, oh, there's a 2 here. So it's 2 times, this is going to be a root 2 over 2, but it's negative because it's in a third quadrant. So this is going to give a negative square root of 2. Your y value is going to be 2 sine 3 pi over 4, which is going to be a 2 times, I think this is positive root 2 over 2. So that's just a positive root 2. And then you have a z value of this. So your point is going to be negative square root of 2, positive square root of 2, and about 11.65685. Okay, so I think that will be our maximum. And we have our minimum value at negative 4/3. So I think the answer here, the absolute min, is negative 4/3. That's 1.33, what is it? 4 decimal places, so 3333. And then our maximum value happens here, 11.6569, positive 11.6569. Okay. Again, we ignored these other points because they do not contribute to our absolute max and min. Now, I did want to show a picture of this that's actually happening in with the surface that we have. So this is the surface that we have. It is an elliptical paraboloid. It's rotated a little bit. The ellipse is rotated a little bit, and the center point is is also moved. Has also moved. And so, if we add on the constraint looks like this. In 2 dimensions, it looks like just a circle, radius 2. But if we see it extended up to 3 dimensions, then we can see the points that we're interested in. Looks like we are interested in, if we follow a path around here, we see a largest z value where the cylinder and the paraboloid intersect. And then we have some small z values here touching the xy plane. Those are the z values of 0, and a slight uptick over here of a z value. And then down in the bottom gives the lower part. And so remember, our critical point happened at 2 comma or 2/3 comma negative 2/3. And so if I put that into the function, I get that negative 1.333. That gives me that point down here, which is going to be within this circle. It's going to give us the maximum or the minimum value. Now, if we shift our idea from this cylinder to the actual circle, just down on the xy plane, remember that this is our domain. Let's see, let's make this a little bit translucent so that we can see the circle. So we can see our minimum is happening over here at negative 2/3 comma positive 2/3 comma negative 2/3. And now we'll attempt to find our maximum and minimum values. What we're actually doing is we're projecting this circle, this parameterized circle, up onto the surface. So it has the same x and y values as in the parameterized curve, but then we add on a z value that's going to be f of r of t. So remember, the chain rule helps us find derivatives of that. So if we see that being projected up, if we look at it directly down on the xy plane, we just see the circle. But if we look at it from a 3-dimensional point of view, we see that it actually is being projected up, and we're seeing those maximums and minimum values. Now, to help us find those max and min values, I think we've noted that the maximum value happens when x is equal to the negative square root of 2. So it's negative square root of 2. And then the y value is the positive square root of 2. And then the z value is putting this these points into the function. So f of those things, which is that 11.656 point. And if we look at it from a 3-dimensional angle, we see that it is in fact the maximum value for that point. We can also plot these other points that we're kind of looking at here, the slight uptick. If we compare these two graphs side by side, this is like a 2-dimensional version. This is a 2-dimensional version of this graph over here. So we can see it starts at 0 and then it goes up. I think I have to look at where the positive x-axis is here. So this is where it begins. So it starts at 0 and it goes up high and then comes back down. And as we go around in the circle, it touches down at the xy plane, goes up a tad bit, and comes back down. So if we see that and compare it to this, we can see the starting from 0 right here, going up to the top, coming back down, touching the xy plane, and going back a little bit, and then coming back down again, touching the xy plane. So it's looking at this 3-dimensional curve that's going around in a circle and looking at it as if it was flat and 2-dimensional land, and then finding out our max and our min values. Okay, so that's it. That's the picture, and I hope that helps, and good luck.